So today we're going to resume our discussion here with Chapter 16, finish this off pretty quick, and then move on to Chapter 18. Hopefully you guys have those notes with you and ready to go. Again, Chapter 16 is sort of, maybe feels a little disjointed to you. It's kind of just a hodgepodge thing, collection of sort of topics to be aware of with confidence intervals and hypothesis tests. So just a few more details to get through today, and then we'll move along. So just remember that in Chapter 14 we learned about confidence intervals. Chapter 15 we learned about hypothesis tests, and then we're kind of in this chapter thinking about some practical issues here. So we're going to jump back in here. I think this is on the middle of page 3 of your Chapter 16 notes, if you're following along there. Just to kind of again relate the idea of hypothesis testing to the justice system. We kind of use this as a motivating thing. When we started hypothesis tests back in Chapter 15. And just kind of a little table here of what could possibly happen. So if we imagine that we're in a courtroom setting, maybe you're on the jury, think about it that way, and you're part of some trial, maybe somebody's shoplifting. Nobody's got murdered this time, so we're just shoplifting. And yes, you definitely should get extra credit for coming in when it's below freezing. I agree with that. Anyway, suppose you have someone on trial for shoplifting, and you have the trial, and again, you as the jury can make one of two decisions, right? You can either declare that person guilty or not guilty. When in fact the person who's on trial, the defendant, the truth, which we won't actually know unless we have video of them doing it or something. That person is either innocent or guilty. So this little 2x2 table has kind of the possible decisions that can happen as a result of this. So if the person is actually guilty and you declare them guilty, then you've made the correct decision. If they're innocent and you've declared them not guilty, then you've made the right decision. But there's these two errors where they're actually innocent, but you declared them guilty, or they're actually guilty and you declared them not guilty. So just kind of thinking about this is kind of what could happen. You can either make the correct decision or you can make the wrong decision as the jury. And the same idea is true of a hypothesis test. So again, the decision that you make based on the data, again over here on the left side, you're either going to reject the null hypothesis or you're going to fail to reject the null hypothesis. But then again, the truth about that hypothesis could either be that the null hypothesis is true or the alternative is true. So again, in these same kind of areas, you're making the correct decision if you correctly reject the null hypothesis, or if you correctly fail to reject. But again, you can make these errors as well. So again, you can reject the null hypothesis when it's actually true, or you can fail to reject it when it's actually not true. And so these errors have names here. So the first error that we see there is the type 1 error, which we're calling alpha, and then we have the type 2 error, which is beta. We're going to call that beta. And so just to kind of define again what these things are, we're not going to spend a lot of time talking about this, but this is sort of things to be aware of in a hypothesis test. Type 1 error, again, is the same thing as our significance level. So that's maybe one reason, if you think about how you might set your significance level, is the probability of making a type 1 error, that is rejecting the null hypothesis when it's actually true. If you want that to be small, you would choose a small significance level. If that wasn't quite as important, you could choose a larger one. But that's sort of the maximum allowable error of falsely rejecting the null hypothesis. And then the type 2 error, again, is not something you set. It's something that you could calculate, which we won't do in here. But again, it's the probability of not rejecting the null hypothesis when in fact you should have rejected it. So there's just some terminology here. And the type 2 error is related to the power, which is just the probability of rejecting the null hypothesis when some other value of the parameter is actually correct. So don't want to spend a lot of time on this, but just maybe from our screen time example, quickly point out what these things are in the context of this example. So back to our example with Gavin. remember we took a random sample of 44 days and we found that his average screen time on those days was 7.3 hours. And again, we were testing the null hypothesis, is that his mean hours of screen time per day was 6.1 versus the alternative hypothesis, which was that mu was not equal to 6.1. It was either smaller or bigger. We didn't care which one, just that it was different. So then, just in this example, quickly, we want to just kind of write out what alpha, beta, and the power are here. So again, alpha is the type 1 error. So again, thinking about this is one of those cases where we've made a mistake. We've rejected the null hypothesis when we shouldn't have. So what this says in this example is that we reject the null hypothesis that the mean is actually equal to 6.1 when it was actually true. So maybe the average amount of time that Gavin looks at a screen is actually really close to 6.1. We just happen to choose 44 days where he watched more TV than usual. So that's an error that we could have made. So that's our type 1 error. Again, beta is our type 2 error. And again, this is we've made an error. So the type 1 error is that we reject the null when it's actually true. This second error is that we fail to reject it when it's false. So let's say what that means here. So that means that we fail to reject the null hypothesis when the alternative is actually true. When the alternative that mu is not equal to 6.1 is actually true. So again, just kind of labeling what these two errors that we could possibly make are. And then up here, I'll write the power here would be the probability of rejecting the null hypothesis for some value of the mean, or some value of mu. So again, we're not going to spend a lot of time talking about what the power is. But again, so we're saying that the mean is either equal to 6.1 or it's not, but we could kind of figure out what the probability of rejecting that is for some other value. So if the mean was actually 7, what's the chance that we would actually reject the null hypothesis? And that can be of interest, although we won't really get into that in this class. So again, just throwing some terminology at you here more than anything, just to have some familiarity of what we're talking about here. I think that officially brings us to the end of chapter 16. Any questions, comments on chapter 16, what we covered? Okay. Well, again, sorry if chapter 16 felt a little choppy. Again, it was sort of just a collection of additional topics that we wanted to kind of make you aware of. So, putting chapter 16 away, let's move along to chapter 18. In chapter 18, we're going to be talking about inference about one population mean. So you might be saying to yourself, haven't we been doing this in chapters 14 and 15? And the answer is yes. But we're going to come back to some of the issues that we had earlier that we sort of pushed under the rug, and actually have some more practical ways of going about these things. So if you remember back to chapter 14, and this is not officially in your notes, I don't believe. Just wanted to remind you where we came from. When we were sort of talking about, when we first introduced confidence intervals, we made these three sort of assumptions. So first of all, we said that we have a simple random sample. There's no other really issues going on there. The second one we assumed was that the variable has a normal distribution. And then finally, again, we're in this case where we're trying to estimate the population mean or say something about it. So we don't know what that is, but we do know what the standard deviation is, sigma. So again, we had a brief discussion about how reasonable these things are. Again, the first one's maybe it's hard to get a simple random sample, but it can often be assumed, or maybe we can hope that we have something that's representative anyway. So that's at least reasonable. Number two, the variable has exactly a normal distribution. Again, that's not a big problem either, because we have the central limit theorem to use. So again, if our sample size, if n is at least 40, we can kind of get around that one in the context that we're looking at here. But this third one is kind of the one that we've ignored and haven't done anything about, and can't really do anything about. So again, this kind of completely ridiculous that we would know what the standard deviation is without knowing what the mean is. So we kind of want to address that issue now. So jumping into your notes here, this is a little bit down that first page. In chapter 14, what we kind of decided upon was that x bar, the sample mean, is a good estimate of the population mean mu. That was kind of our motivating example for how we started our confidence interval. So again, if we think about this more realistic situation where we don't know what sigma is, we don't know the population standard deviation is, you could think about sort of the same idea, that we can use something from our sample to estimate the population quantity. So what we can do is you can use S, which is our sample standard deviation, to estimate that population standard deviation. So back in chapter 11, when we assumed that sigma was known, we used this Z formula, x bar minus mu divided by sigma over the square root of n. And under certain conditions, we knew that follows a standard normal distribution. That was either the central limit theorem coming in to help us, or if the population was normal. So again, kind of the corresponding idea here. So in the we put ourselves in more of a real world setting. When sigma is not known, we can just kind of throw it into that same formula. So instead of dividing by sigma over the square root of n, we can divide by s over the square root of n. And remember, so this is the sample standard deviation, which we calculate from the sample. So we always know what that is, right? Kind of just like we always know what the sample mean is. We always know what the sample standard deviation is. So instead of the formulas on the previous page, we can use this formula. As we're taking x bar, we're subtracting off the mean, and then dividing by s over the square root of n instead of sigma over the square root of n. So that's all fine. We can do that. There's no problem there. But there's one catch, is that this thing doesn't quite have a normal distribution. So again, what we saw on the previous page is when we have a z, x bar minus mu over sigma divided by the square root of n, this thing is normal with mean 0 and standard deviation 1. It's a standard normal distribution. But the problem is that this thing we're calling t up here, x bar minus mu over s divided by square root of n, is not quite normal. So we have to change our strategy just a little bit. And this is something that's called the t distribution. So again, if we kind of the usual assumptions, if we have a simple random sample from a large population that has a normal distribution, so again we're starting out with the assumption that our population is normal, then this thing which we can call the one sample t statistic, so it's just called the t, has something called a t distribution with n minus 1 degrees of freedom. And so we're going to take a look at kind of what is that distribution. So just before we take a look at what this distribution looks like, just another quick note is that when we're estimating the standard deviation from the data, the result is called the standard error. So instead of calling it the standard deviation, we're going to call it the standard error. So the standard error is an estimate is an estimate of the standard deviation. Just to kind of keep our terminology straight, we're going to call the estimated thing, we're going to call that the standard error, and we'll call the actual thing the standard deviation. And just remember, so the standard error is our estimate, so that's s over the square root of n, whereas the actual standard deviation we know is sigma over the square root of n. So again, sigma over the square root of n, that's not estimating anything, that's the actual quantity. And this estimate of it we're going to call the standard error. And then we're going to use this thing to kind of do the same thing that we did before. We're going to use this to make confidence intervals and do hypothesis tests. And I'm going to kind of look at what we mean here by what this t-distribution is. So this picture is in your notes. It's also in your textbook, I believe. And here we have a plot of two different t-distributions, as well as the standard normal distribution. So the solid line here, this is the normal 0, 1 distribution, and then we have two different t-distributions here. One has we'll put a subscript of a 2, and the other one has a subscript of a 9, and that refers to the 2 and the 9 refer to the degrees of freedom. So don't need to worry too much about what degrees of freedom means, but that's some new terminology that we'll have to be using here. So as you can see from this picture, the t-distribution looks very close to the normal distribution, right? So if we have the solid line again is the usual thing that we're used to looking at, and the dashed lines you can see are very close, right? So it kind of has that same shape. There's maybe a little difference going on there, but keeping your eyes on that picture, who can help me out with some similarities and some differences here? So how are these? How is the solid line and the two dashed lines? How are those similar? Anybody have any ideas? Yeah. Yeah, exactly. So they both have that symmetric shape we're used to seeing. So they're both symmetric, and yeah. What else? How else are they similar? Yeah. They have the same mean, exactly right. So they're both centered at 0. They have the same mean. Very good. And we can also say they're both sort of bell-shaped. They're both unimodal. All those things that we like to talk about when we're talking about shape. So that's how they're similar. So how are they different? Again, kind of looking at this picture, how are these things different? Yeah.
As that box so nicely points out, there's more area in the tail.
Exactly right. So if you're paying attention, then you can pick this information up from the slide, right? So the difference is that the t distribution has something we'll call heavier tails. This just means that if you get out into the tails of the distribution, so as you move further away from 0, these things are higher up here than the standard normal distribution is. So that's kind of the main difference, but also just note that that the t distribution depends upon the degrees of freedom. So the t-distribution has this extra thing that we need to think about, which is the degrees of freedom. And as you can see from the picture, when the degrees of freedom are different, the curve looks a little bit different. Again, it's very, very similar there, but it is slightly different. So it has this extra thing that it depends on unlike the standard normal distribution. And if that sun gets bad, you guys out there, let me know. The reflection from the over here looks like it's creeping in. Okay, so that's so again, these two things are very similar, but they are slightly different, and so we want to make sure to pay attention to these differences, and do something about them. So again, kind of keeping your eye on that same picture, you can see that the t distribution with 2 degrees of freedom is the one with the thicker dashes, and that has heavier tails. And as you go down to the 9 degrees of freedom, you're getting less heavy in the tails. So, question: what would you anticipate happening to the t distribution as the degrees of freedom get larger? So, what would you anticipate happening to the sort of the edges of the distribution? Yeah.
It's closer to the normal.
Yeah, exactly right. So, so the response was that it gets closer to the normal curve, which again you can kind of see that happening in the picture. So as the degrees of freedom get larger, the t distribution gets closer to the normal distribution. Very good. So I just had a question come in on the back channel. Do the curves still have the same area under the curve? So maybe we could put that on this chart as well. What do you guys think? Are they going to both have area 1 underneath those curves? Seeing maybe some nodding heads. So we know the z distribution has area 1 under the entire curve, right? What about the t distribution? Why does that, or why doesn't that have area 1 underneath it? Any ideas? Yeah.
I would say that because if you increase your degrees of freedom to like infinity, it'll be the same as a normal curve.
Mm-hmm.
So as you like adjust it, the t distribution gets shorter, but also gets heavier tails.
Yeah.
And variables.
Right. So kind of the way of seeing that is that so for example, if you compare the heavy dashed line to the solid line, there's more area out here, but less area up in here. So yes, they will both still have area 1 underneath them, and that's because they're both a distribution, right? So it's kind of like the total possible area under the curve, under a density curve, is always going to be 1, regardless of what distribution it is. So yes, they both have area 1 under the curve. That's a great question. So yeah, so then we can see there here as it gets closer, as the degrees of freedom get higher, the middle part gets higher, so it gets closer to that normal curve, and the outside part gets kind of flatter and flatter, so that kind of think about that area will equal out. All right. So before we give some formulas here for doing inference on a mean, before I give you the formulas for actually doing the confidence interval for a mean, kind of want to go back through some conditions. So maybe before I do that, I don't know, maybe if you're starting to feel a little confused by all the different conditions that are flying around out here, I'm going to put together a document maybe over the weekend or beginning of next week that kind of really steps you through when to use which conditions, and I'll send that around next week because I think it can get confusing about what conditions are we using when. The notes haven't always been perfectly clear, so I'll make sure to clarify that better next week. But anyway, the conditions that we have that I'm going to give you right now that are in your notes at the bottom of page 2 there are going to kind of be the gold standard for the conditions. So if you ever have a question about which ones I'm doing, you can go here. So again, I'm going to have the same 3 conditions, but what we have to check in each one is going to be slightly different here. So we have the same random sample condition, and this is actually exactly the same as it was before. So we just want to make sure, do we have a random sample, or at least is it a representative sample, or is it coming from some sort of a randomized experiment? So that's kind of just the gold standard that we're always hoping for, and it's often stated in the problem. If it's not stated, you have to kind of think about where did this information come from, and might it be reasonable to assume that it's a random, or that it's a representative sample. So that's our first condition. That's kind of the same thing. The second condition is actually going to be the same as well. So the small enough sample condition is going to be exactly the same. We want to make sure that our population of interest is at least 20 times bigger than our sample. So again, if again n is our sample size, just to refresh you here, we want to make sure 20 times n is less than the total population. The total population size. So again, first 2 conditions are not have stayed exactly the same. So those are okay so far. When we get over here to the large enough sample condition, things change just a little bit here. So I want to talk about what's going on here, and maybe a more complete list here would include a question first: is that are we assuming sigma is known? So again, here in this chapter, we're assuming that sigma is not known. But if it is known, then we can kind of think back to what you were doing in chapter 15. So here we're assuming it's not known, but you might get a question thrown at you that tells you what sigma is. So here in this chapter, and kind of in this is more the real world situation, is that we're assuming that sigma is not known. So the first question that we want to ask is are the data coming from a population that has a normal distribution? So if the population is normal, then we're good to go. So if you're in that sort of rare case where that is the case, you're ready to roll there. But if not, then we have instead of just saying is n bigger than 40, we have a few other cases we can talk about here. So if you jump down to this last point here, so here in this chapter using the t distribution, if n is bigger than 40, then we're sort of always good to go. So if the same as before, if the sample size is at least 40, you can always use the procedures that we'll talk about here in just a minute or so. Kind of like we did before. The difference is now that if your sample size happens to be less than that, there's sort of these intermediate cases that you can be in, and it depends on how close to normal is the data that I have. How close to normal is the population that I'm looking at. So again, if the distribution is normal, then we're good to go for any sample size. Let me add that in there. But again, if it's not, then if the sample size is less than 15, we can use these procedures if the data is close to normal. So if it's kind of has that sort of symmetric shape that we're familiar with, is it single peak? Are there making sure there's not any crazy outliers? And again, if any of those things are there, then we kind of want to shy away from using the t distribution. If our sample is a little bigger, kind of in that middle ground there, if it's between 15 and 40, we can use this procedure except in the case of extreme outliers or really strong skewness. So again, we're kind of stepping up to this. If your sample happens to be less than 40, then we sort of need to think about is the distribution I'm working with here normal? And what that requires is you have to actually look at the data. So make a histogram of the numbers that you have or something like that from your sample, and and see kind of is it something that looks close to being normal. And so if you don't have the data, then you can't look at it, obviously. So in that case, you'll just need to be a little bit more cautious. So again, the large enough sample in this chapter anyway is kind of this. We have three different cases that we can have. If our sample is really small, if it's less than 15, we need the population to be very very close to normal. In the intermediate case, we can have some outliers or some skewness, but if it's really bad, then that's not a good thing. But if your sample is big enough, if it's at least 40, then we're always good to go as far as this condition is concerned. And so the actual numbers that we chose, like the actual numbers 15 and 40, are somewhat arbitrary. It's just kind of giving you good sort of benchmarks to think about there. And again, just note that this third condition is a little different. And just to remember that if one of those conditions does not check out, so if your sample is not random, if you're not told that it's random, or you can't assume that it is, if your sample is too big, or if it's not large enough, then kind of the procedure that we'll use in this class is to proceed with caution. So again, remember, we're using these conditions to check to see if these procedures are appropriate to use. And again, if you're in the real world, if the conditions don't check out, then you sort of don't have anything to do. For the purpose of this class, we want you to go ahead and do the calculations anyway, just to kind of see what the results are going to be, but just make a note to proceed with caution, or give it the old PWC. And that's okay. But again, in this class, just go ahead and do the calculations anyway, just to kind of see what the result would be if you could do the procedure. All right. Any questions on what we're talking about here so far? Where are we going? Right. All right. Well, let's figure that out. So just a quick note on Table C. So you have a little bit of Table C on the third page of your notes. The whole thing is on the last page of your notes on page. What is that? Page 10, I believe. We've got a little ways to go in this chapter yet. But where we're going here, let me just jump ahead real quick. Where we're going here is this formula right here. This is the bottom of page 3. If we're going to do a confidence interval in this case where we don't know what sigma is, our formula is going to be this thing, which looks very similar, does it not, to x bar plus or minus z star times sigma over the square root of n. So it looks very, very similar, kind of the same idea. We're taking our estimate x bar and we're adding and subtracting something to get our confidence interval. And so we had a brief discussion on what z star was. That was our critical values. We're going to need to do the same thing here using the t distribution, and the procedure is a little bit different for figuring out exactly what t star is. Well, the distributions are different, right? So those critical values for the t distribution will be different than they are for the z. And so this is where the table comes in handy. So you can start looking at the table there. But just some notes about it. Just note that it is different than Table A. So Table A, you look up a z-score, you find a probability, and you go from there. Table C actually just gives you straight up what the critical values are. And again, remember, it depends on the degrees of freedom. So whatever that is for your example, that's the line of the table you want to use. You'll note at the bottom, the very bottom row of that thing, maybe you can see it better on the last page of your notes, has the common confidence levels for the z. And before we look at it here, just maybe this final note that is, so to find what your critical value is, you're going to have to figure out what the degrees of freedom are, and it's possible that your degrees of freedom will not be listed. So if that's the case, and I'll kind of show you what we're doing here, you want to round down. So regardless of what your number is, you want to go to the next smallest number that's given to you on the table. So question came in, sorry, I'm just now seeing this. On the homework and exams, will it explicitly state normal, or will we have to check the conditions, the sample size to determine that? Great question. So if it doesn't tell you that it's normal, and if your sample size is less than 40, so sorry, going back real quick here. If you're in one of these two cases, on a homework or an exam or something, well, on a homework you might be given the data set and you'd have to make a histogram and you could look at it. And I think the example that we're doing here is not that way. But one we'll get to later in this chapter is where we'll actually look at the histogram to kind of see, is it close to being normal. On an exam, if you were asked to do that, if you were in one of those, the two conditions, the really small or the sort of medium-sized sample, you'd be given a histogram and say, and use that if you need to say, is the population sort of close to normal or not. So if it's not stated that it's normal, then you'll just have to use either hopefully your sample size is bigger than 40 and it doesn't matter, or you'll be given a histogram and be able to sort of figure that out on your own. Let me know if that didn't answer the question. Is that okay with everybody? All right. Okay, so just quickly to point out here on the table, what this table gives us, again, remember, is the critical value. So what's actually inside the table here? This is our T star. This is our T star values. So again, this is very different than the standard normal table that we looked at before. So we're going to calculate. We're going to figure out what our degrees of freedom. Remember, the degrees of freedom is n minus 1. So however many people are in your sample, that number minus 1. So that's going to be the row that you go to. So say that I end up with, say I end up with 30 degrees of freedom. Say I have 31 people in my sample, so the degrees of freedom is 30. And then this just gives me the critical values for that situation. So if I want a 95% confidence interval, I would use 2.042. If I wanted a 99% confidence interval, for example, I would use a slightly larger number, and so on there. So again, kind of the usual columns that we looked at before were the 95%, the 99%, and the 90% here as well. This table does list a bunch of other ones as well. So if for some reason you wanted a 96% confidence interval, those numbers are all right there as well. So just key difference is that this table is actually giving you the T star value that you need. You just have to pick out the right row, and then the number is right there. So, and then note down here at the bottom, again, as the sample size gets bigger and bigger, you can see these numbers get closer and closer to the 1.645 and the 1.96 and the 2.576 that we've seen before. So again, the T distribution gets closer to the normal as that degrees of freedom gets bigger. Another question, will we have to memorize all the formulas for the next exam? I think he's going to do some sort of formulas like he did on the first exam, but most of them you'll have to commit to memory. That's correct. All right. So coming back here to what our formula is, same kind of setup as we had before. That if we take a simple random sample of size n from some population with an unknown mean, the level C confidence interval, so whatever that level that we're interested in, 95%, 83%, whatever you want it to be, is going to follow this form. So we're going to take our sample mean, add and subtract now a T star times S over the square root of n, where that T star comes from that table that we just saw. So again, the interval, just a sort of a note here, is that when you have a normal population, this is going to be exactly an exact interval, and if it's again, if you go through the conditions and those all check out, it'll be close enough to go ahead and use. So just keeping that formula in mind, remember this is kind of our practical formula here, right? It'll almost never be the case that you actually know what sigma is without knowing what mu is. And so this is what we can actually use in a more realistic setting. But then again, just to note that it is similar to our previous form. We're taking our estimate and we're adding and subtracting the margin of error. So again, in chapter 14, it was x bar plus or minus z star times sigma over the square root of n. Here in chapter 18, it's x bar plus or minus t star times s over the square root of n. So same idea, just changing the formula very, very slightly there. All right, let's go ahead and actually do an example here, kind of show you what we might need to do here in this chapter. So we're going to go back to the IQ example. Suppose we take a random sample of 5 adults, and they find that they have a average IQ score of 100, so an average IQ score. And for now, we're going to say the data appeared to be approximately normal. So maybe we looked at a histogram and could tell that was looking pretty good. And so we want to compute a 99% confidence interval for the average adult IQ score. So that would be our mean mu in this case, is that average adult IQ score. So kind of stepping through this formal 4-step process really quick. The first thing again to think about is just what do we want to do here, and this one's pretty straightforward, so I'm not going to write it down. We want to know what the average adult IQ score is, and so we can do so using a confidence interval. Well, I'll go ahead and put it. So just what do we want to know? We would like to know the average adult IQ score. I was taking what's said in the problem and translating sort of what's the practical question that we have to deal with here. And then sort of maybe overstating the obvious here, but we will estimate the population average IQ score, which is our mu, by constructing a 99% confidence interval. So again, we want to know what that population average is. So to give a good guess of what that is, we're going to do a confidence interval. So just kind of reminding you the formal process of what we're doing here. All right, so we're ready now to solve. We kind of have our question in mind and kind of know what we're doing here. What's the first thing I need to do in my solve step? It's your favorite thing to do. Check conditions, right? So the first step is we want to check our conditions to make sure that we can actually go ahead and use this formula. So again, same 3 conditions as always. Random sample, small enough, and then large enough. All right, and we've all done this a few times now. So do we have a random sample? Well, yes, we do. It's stated. So we take 20 times n, which is 20 times 5, which is 100. And are there more than 100 adults in the world? Well, yes, of course there are. So this is less than all adults. So again here, large enough sample, the n is equal to 5. So what do we do if n is equal to 5? Or what can we do here? Yeah.
Stated that it's normal, so
Yeah, right. So kind of thinking back, I'm not going to jump all the way back to it, but that on that slide that we had our sort of three cases for the large enough condition. We're in that smallest one, right? N is less than 15, but what the problem tells us is that the data appears to be approximately normal. So because it's close to being normal, we're okay here, even though the sample size is very small. So N equals 5, which is less than 40. So we need to think about, is it okay? But we're okay because the data is approximately normal. So a check, check, and a check. Good to go there. Moving on to, I don't think I have enough. I didn't make another. We'll still pretend we're on the solve step here. So now we can go ahead and actually calculate what our interval is. Because our conditions checked out, we're okay to use this procedure. So again, remember our formula is going to be x bar plus or minus t star times s divided by the square root of n. And I'm just realizing that there's a little typo on your example with a standard deviation of 15. So this is S now. So for those 5 people, the standard deviation of those 5 numbers is 15. Sorry, that's a little omission there. It was unintentional, I promise. Okay, so again, making kind of a list of what we need to know what the x bar is, we need to know what s is, we need to know what n is, and we need to know what t star is. I'm also going to write down what our degrees of freedom are. So again, from the example, we know that our sample mean is 100. We have 5 people. The standard deviation of those 5 numbers is 15. And our degrees of freedom is 5 minus 1, which is 4. And remember, we want a 99% confidence interval. So what I'm going to do is I'm going to go back to the table. Kind of get rid of some of these things here. So again, I found what my degrees of freedom is 4. So I'm in this last row that's given there on the first part of the table. And there's the rest of the table kind of fills in some more of those numbers. I just left it out for purposes of space. If I want a 99% confidence interval, I just need to go in the row that's 4 degrees of freedom and just pick out the number that's there in the 99% column. So again, when you're working on your homework, that table is in your notes. It's also in your textbook, kind of close to where the other table is. So that tells us that our t star is going to be equal to 4.604 because I want a 99% confidence. So have all my numbers here. I'm ready to roll. I can just plug these things in. I have 100 plus or minus 4.604 times 15 divided by the square root of 5, which is the same as 100 plus or minus 19.94, which is 80.06 to 119.94. So there's my confidence interval. What's the last thing that I need to do? Again, I've done my calculation. Am I done? I'm not done. What else do I need to do? Conclude, right. I need to give an interpretation here. So the same interpretation is going to hold. What we'll say is that we are 99% confident that the average adult IQ score is in that interval. So it's between 80.06 and 119.94. Same interpretation as before. We are blank percent confident that whatever the mean we're looking at lies in that interval. Any questions you guys can think of on what we're doing here? Yeah.
So like we're doing a problem individually. Do we still say we are 99% confident? Say I am?
So the question was, if I'm just doing this problem by myself, do I need to write we? So again, here we're doing this problem, right? So we have concluded this. You can say whichever one you want. If you want to say I am 99% confident. Kind of the convention in science, I guess, is to say that we have concluded, because presumably if someone else did this correctly, they would get the same answer. It's kind of where that comes from. But if you want to put I am, that's fine too. Yes, good question. Well, I think we're out of time, but thank you guys so much for being here. Bonus points, definitely, at least in my head, that you were here when it's so cold out. And have a good weekend, guys. We'll see you next week.